This is Mrs. Ross. I am here to go over, actually start chapter 8, and today we're going to go over sections 8.2 and 8.3. This is what we're going to work on more while I'm out the week of February 13th. So this is a new chapter. The chapter is called Rational Functions, and I want to start off with a couple concepts before we jump right in. The two concepts that I want to kind of go over, oops. Sorry about that. Okay, what is a rational function? So if you look in your book, a rational function is not written like that. Let's go back. Okay, a rational function is written like f of x equals p of x over q, that's a q, q of x. Okay, and q of x cannot be 0, obviously, because if it was 0, then we would have a 0 in the denominator, and we don't like that. And it's p of x and q of x are polynomial functions, and it's basically the ratio of two functions to each other. So that's the definition of a rational function. It's the ratio of two polynomials. And today we're going to talk about one specific type of rational function, and that is an inverse function. So very, very simply, if you think back a long time ago, chapter 3 or chapter 4, we talked about things that were a direct variation. So this was like when y equals x, right? When x went up, y went up, and they varied directly. So this is a direct variation. If we graph it, it looks like this, right? Direct variation. Now in 8.1, which we are going to go over when I get back following week, we're going to learn about something called inverse variations. So if a direct variation is y equals x, and inverse variation is y equals 1 over x. Okay, or we could have, instead of 1, we could say this is a, right? A constant a. But basically, you can see inverse, you know, the inverse of a fraction is where you flip to the numerator and the denominator. So the inverse function is where your y and your x are on different, you know, your y is in the numerator and your x is in the denominator. So they're inverses of each other. So we'll learn some more about dealing with inverse functions again in 8.1 when we come back next week. But 8.2 and 8.3 are all about graphing inverse functions and rational functions. So that works perfectly for a call like this. So let's flip over to Desmos. I think I still have Desmos up, I do. And let's just look at what an inverse function looks like and some of the different features of them. Again, just a reminder, this is a direct variation, not an inverse variation. This is our inverse variation, y equals 1 over, with that. There we go. That's what I was trying to get to. Okay, so what you'll see here is when you have y equals 1 over x, you get this kind of curvy looking graph, and we call this kind of a graph a hyperbola. Two symmetrical parts called branches. This branch is symmetrical to this branch. Looks like it's a symmetrical about y equals negative x, right? And there's a couple things that we notice that are interesting about this. Okay, one is that this graph has two asymptotes. Now that's another vocab word to remember, right? An asymptote is that the graph can get really, really, really close to, but never quite make it to. Particular graph. If we look at the domain of this graph, remember the domain is all your x values. Okay, anything except for 0. So we would say the domain of this is except for x equals 0. And that makes sense, right? Because if f, then it's 1 over 0, and people don't like 0. So what about y? So now we go to our y-axis, right? And it looks like y can be any value except y can never be 0. And why is that? That was a lot of y's there. Well, if you think about, and I can't draw right on here, so I'm going to have to come back over to paint here. Okay. If you think about what we have graphed, we have y equals 1 over x. Obviously, x cannot equal 0, right? Because if x equals 0, then we have the whole problem of 0 in the domain. Why? It looked like y could not be equal to 0. Now, why is that? Not 10. Y could not be equal to 0. Why can y not be equal to 0? Well, think about it. If you have x equals 1, it's going to be 1 over 1. So that's 1, right? If you have x equals 1 over, I don't know, 1 over 100,000, right? That actually is a number. It's a very, very, very small number, right? But it's 10 to the negative 5th, I think. No, negative 6th, I think. Negative 5th. All right, it's 10 to the negative 5th, but it's still a number. It can never big. You make your denominator, still going to end up really, really tiny number. If we go back to the graph, if we wanted to talk about the domain and the range of this graph, this is a graph of the inverse function. It's called a hyperbola, and the domain is all reals except x equals 0, and the range is all reals except y equals kind of the y as to why that is. Now, there's a couple ways that we can transform our graph. We can make our graph negative, so let's look at that. Okay, so when we make our graph negative, you can see that it flips about the x and the y axis. So that's what the effect of a negative number is. We can also, what happens if we, let's say, add 5? So if we have equals 1 over x plus 5, then you can see that the whole graph shifts up. So our xb, our domain can still be right, because we still can't put 0 in there because 1 over 0, always bad. Okay, can we put in domain? So what about our y's, our range? Our range looks like it's all real numbers except for when y equals 5. Y can't equal 5 because you're always going to have, no matter what number you put in for x, it's always going to be 5.0000001, right? It's always going to have some value. You can never make 1 over x exactly equal 0, and therefore you can never make this function exactly equal 5. Okay, what happens if we put, instead of adding 5 there, if we add 5 into the actual inverse number? So this is going to shift our graph to the left, right? So I should say. So now when we look at the domain, it's going to be all real numbers except x cannot equal negative 5. And why is that? Well, negative 5 plus positive 5 is 0, and then we have that whole problem of 0 again, right? And then our y values, when we look at our range, so our range is our y's. Go along here. It looks like our range is going to be what? Our range is going to be all values except for when y equals 0. So we can never get it to quite get to 0. No matter how big of an x that we get, we can never get our y value, or how small of an x we get, we can never get our y to get to 0. Okay, so then when it comes to the homework, what we're going to do is we're going to be graphing these functions, and then we're just going to be talking about what the domain and the range are. So I have this on your homework sheet. really do all this work in Desmos to see where my domain and range are. So domain is -4 divided by x. Okay, so we have this graph, and I can put up over x just so you can compare, or I'll even do negative. Okay, so you can see when we have the 4, it's just multiplying times 1 over x. So we have things that are growing more quickly. Okay, so when I look at the domain of f of x equals x, the domain my values. Let's say that the domain of this is all real numbers except for x equals 0. And that is because x equals 0 is my asymptote, right? Then if I look at my range, so my range is my y's. Looks like it can be n, right? All the way down here. And then my range is going to be all y's except for y equals 0. It's because whatever number I put in here, huge number in my denominator, and I divide, 4 divided by 1 million, I'm still going to have some small tiny number. I can never get my function to be y equal, or f of x. So we would say, if I was doing this problem, I would show this graph, and I would say the domain is all 0, and my range is all reals except x equals 0. So let's do number 2. We have y equals 8 divided by x. Draw on here for you guys. Okay, so zoom out a little bit. Maybe we can see even a little bit better here, right? Look at my domain. My domain is my x's. So I have -20, x can be -10, -10, -5. Up when I get to 0, x, real x's, right, equals 0. I have an s right along the y-axis. It's my range. My range, so looks like good. I get to negative, and there's an asymptote there to equal -5. So my range is going to be all real numbers except for -5. And this makes sense because even if I have 8 divided by 1,000,000, I still can never get my value to be 5. It'll look close in your calculator. Don't get me wrong. If you scroll along here, you can get really close to 5, but you're never actually able to make the function get to 5. Okay, so let's do example number 3. We have 1 divided by x minus 3 plus 2. Let's move back to our graph here. So we've got a couple things going on here, right? Let's look at our domain first. Our domain is our x's. So x is good. And then I get to x equals 3. And I have an asymptote here at x equals 3. Get my function, value of my function when x equals 3. 3 minus 3 is 0, and we know that's bad. My domain is going to be all x's except for x equals 3. Let's look at our range. So our range, good. And then I get here to y equals 2. Total y equals 2. Okay. So it's going to be all real numbers except y equals 2. 2 plus some number, and this number is always going to have a value. It can never be 0. My range is all for y equals 2. that's kind of how we do that. We're going to get into some more complicated looking functions, and we can see what those look like. So we did 1, 2, and 3. We're going to do fix and the denominator. First 3 examples, x was only in the denominator. So I had basically a simple inverse function. Now I have x in the numerator and the denominator, so you can kind of see how those play with each other on the graph. So the first graph I have is x minus 1, and then let me just do these separate, plus 3. Okay, and we're going to combine these two together. So we have y equals x minus 1, x plus 3. So let me hide these other two. So here is my combination of the two. Play with my asymptotes a little bit. I still have a hyperbola, right? I still have my, let's see where the asymptotes of these equations are. All right, maybe I'll zoom out a little bit so I can kind of play with it. So first I want to look at x, right? X looks good. It's good, 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 good. And then all of a sudden we get to x equals -3. Looks like I never quite get my value to x equals -3. So I think my domain, my asymptote is at x equals -3. And my domain is all reals except x equals -3. I look back at my equation, it's because x -3 3 is 0, and I can't have 0 domain. So get to the same exactly is my where's my asymptote on my y-axis. I need to scroll out a little bit to see, okay, what does this get really close to and never quite get to? And I still haven't quite done it yet. So all the way out here, when x equals 70, y is getting really, really close to 1, but it's not quite there yet. And then on this side, remember, my y value is 0.967. So my y is getting really quick except +1. So sense. Well, that's because of this error, right? No matter how big of a number that we get, we can never force this to become y equals 1. Okay, so let's do 2 more of these kind of examples. Actually, we'll just do, and then I'll skip to 6, 8, or 8, 3. Because I think you guys can probably get this concept. 3x divided. So I've got another hyperbola. Let me zoom back. Right. Let's look at my x's. So what's my range? Good, good, good. My range looks like around what? Never can quite get to -1 is what it looks like to me. So negative of -1 is +1, plus -1 is 0. So my domain is all x's except for x equals -1. My range. My range is a little bit trickier, right? I have to look, well, not really that much trickier. The range is my y's. I need to look on my y-axis. It looks like along here, as my x's get bigger and bigger and bigger, right? My y value gets closer and closer. It's 2.852. It's getting bigger and bigger and bigger. The other way on my graph, 3.2. So it looks like that my y value that I can never get to is y equals positive 3. Right? So no matter what value I put in here, let me just take this. And let's say I put in 1,000,000 here. Put in 1,000,000 for our value. We don't even need our y equals, right? So this is just kind of proving. So we put 1,000,000 in. Our y equals 2.9999950. So we can never quite get to y equals 3. So our would be all y's except for y equals 3. Okay, so 8.3 is graph general rational functions. So before we were only dealing with basically x's that had exponents to them. And now we're actually going to put in some polynomials and see what those graphs look like. So they actually make some pretty. So what I mean by that is, for example, graph y equals x squared plus 2. Okay. It's kind of a cool little graph, right? You get a little bloop. Got a bell curve, actually, which we'll talk about. So what's going on with this graph? Well, rational function. This is a rational function graph that we have. The definition of a rational function is that it's a ratio of one function. In this case, the numerator function is just 4, and the denominator is x squared plus 2. So, excuse me. What we want to be able to do is to be able to graph these kind of functions and look at them and to observe what are the information about this. So for this particular one, I'm actually going to do a print screen and go back over to Paint so I can draw on here a little bit. In 8.3, graph general rational functions state the domain and range. We've graphed this, and now we've got to think about what is the domain and the range. Remember, is our x's. In case our x can be any value, right? If x equals 0, plus 2. And because we have a squared value, we can never have a negative. So, in case our domain, it's an easy, is all real. Okay. So this is no longer our standard inverse function. These are just other. Now we need to look at our range. Our range is actually our range is our y's, and this particular graph has an asymptote axis, right? We can never force this to go below the range, the y's go below 0. So always going to be greater 0. Okay. And then we have our function peaks right here at 2. It has to be less than 2. The question is, can we equal 0 or equal 2? And then we'll need to go back to Desmos and to use our math to kind of figure that out. So if I go back to Desmos and I track along here, x equals 0, y equals 2 is a point. Looks like it's a point on my graph, right? If I think about x equals 0, 0 plus 2 is 2. 4 divided by 2 is 2. That's a valid value. So going back to Paint, y has to be less than or equal to 2. Now, can y ever equal 0? We know it can't go below 0, so let's kind of look at our graph to see. Okay, can zoom out a little, right? going to get really, really, really close to 0, but not quite there. So we can always check this by putting a huge number in here, right? Our good old 1 million. And see, oh, yep. So no matter how big of a number that we have, we're still never going to get 0. So that's how we know, okay, why for this particular graph, the domain is all real numbers and the range is that is greater than or equal to 2. So I have another graph, another example. We have y equals 3x squared divided by x squared. Check out this graph. Let's zoom in a little bit here. Graph, zoom in, has a couple different asymptotes on it. So let me print screen, move that over to here so we can do some drawing on here, okay? Okay, so this particular graph showed at, I should have a different color, line. Okay. X equals -2 equals -1. X equals 1. And it looks like we have an asymptote at y equals 3. Or if I was to draw my asymptotes on the graph, that's where I would place those. So what does that mean in terms of my domain and my range? My domain, again, is my x's, right? Domain for this graph is going to be, okay, x is good, 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 good. I get to x1, and I have an asymptote there. Then it's good. We have a little parabola there, and then value. So my domain, all real, equals -1, and x equals. Right, so why is that? So let's look at our actual equation, right? X equals 1. 1 squared is 1. 1 minus 1 is 0. We have the whole problem of having a 0 in the denominator. When x equals -1, -1 squared is 1. 1 minus 1 is 0. And we have a 0 in the denominator, so it's not possible. So this makes sense from a function, right, as well as an algebraic function. Now we have the range, right? So our ranges are y's. Good, good, good. And then all of a sudden we get to, so let's do range in green here. So range is good. Here we get to 0, right? So it looks like for our range, y has to be less than 0, and we don't know if it can equal 0 yet, right? Y greater than +3. These values up here, greater than +3. Okay, on the so let's look at these a little bit, right? Y has to be less than 0. I'm going to switch back to Desmos for this. So on my graph, value of 0, 0. So if x equals 0, then this becomes 3 times 0 squared, which becomes 0. So 0 divided by -1 is 0. So that is a valid value. Say, yes, y has to be less than or equal to 0. For the other side, it has to be, y has to be greater than 3. Use example number 3 and graph that. So we figured out our asymptotes here, and we figured out our range, right? So let's move to number 3, which is f of x equals x squared, oops, x squared divided by x squared plus 1. All right, so we kind of get this cool looking V-shaped inverse Bell function. And again, let's kind of take a look at this. This one I don't think we need to move over to paint to really get. So let's look at the x's. So it looks like if I follow my x values, x can be anything, right? All the way down to, is x equals 0 a valid point? Okay, so let's kind of look here. X equals 0 would be 0 plus 1. So we still would have a valid value here, right, of -5. And then all the way back up here. X keeps going. All right, so we would say that the domain for this function is all real x's, right? All real numbers. So now let's take a look at the range, right? The range for this number, maybe I should print screen and bring this over. It's not there. Okay, the range for this would be, so domain all real. What's my range? Okay, so my range is that I know that y can never get lower than -5, but it can equal -5. We kind of prove that when we pick the value of x, right? So we have -5. The range is going to be, I think I'm going to have to write this out. Okay, we have -5. Y has to be greater than or equal to -5. We can get a value of -5 if we have x equals 1, right? And then what's my asymptote on the top here? What does this get closer and closer and closer to but never quite reach? Well, if I look at my graph here, it's right here at y equals 1. So y has to be greater than or equal to -5 and less than 1. So let's double check my Desmos graph to make sure that I'm getting closer and closer to 1, but never quite getting there by zooming out, right? This is one way to check. So you can see out here, even with, x equals 38, y can never quite get to 1. Okay, and that's just a function of the way that these two polynomials interact with each other. So if I wanted to graph this, I would graph it like this, and then I would say the domain is all real with 2 L's, real, and the range is -5 is less than or equal to y, which is less than 1. Okay. All right, one more that we want to graph here, and then you guys will be on your way to have fun graphing domain and ranges. We have, this is a nice one, we have a quadratic at the top. Y equals x squared minus 2x minus 3 divided by x minus 4, if I type correctly. So this is kind of a fun looking function that we have here, right? Let me pull this over to paint so I can draw a little bit on here. Maybe. There we go. Okay, so let's look at this function. We've got two kind of looking hyperbola things, but we look like we've got some asymptotes that we have to look at. So let's look at the x-axis first, right? So if I look at the x-axis, it looks like if I look at my values for x for my domain, that there we go, that my function can be any value of x except for x equals 4. And so I go over here, x equals 4, 4 minus 4 is 0. We know that's a no-no to have that in the denominator, so I'm good on my domain, right? My domain is all real except x equals 4. Okay, so that's good. Now let's look at my range. My range is interesting here, right? I don't really have an asymptote, but I do have some values that are kind of missing that I'm not able to obtain. So I might have to switch back over to Desmos for my range. So if I look at my range, right, my y values, so I'm looking at the y's, 23, 21, 19, 18, okay? Looks like my y bottoms out at 10.474, right? And then over here, it tops off at 1.128. Okay, so my y values can be anything. Let me print screen this again. Okay. My y values can be that y, right? Y can be anything less than 1.528, and it can also equal 1.528, right? And my y can also be greater than or equal to any value that's 10.472. Sorry for the messy greater than or equal to. Right? But my y can't be between those two values. So my y either has to be greater than 10.4272 or equal to that, or less than 1.528 or equal to that. The y can't have any value that's between those two values. So we can never have this function have, for example, y equals 6. That wouldn't be possible. Okay, so that is 8.2 and 8.3. Hopefully that all made sense. If not, you can come back with any questions next week. And I hope you guys have a great day. I will see you soon. Bye.